When I go searching Google images for CMBR, I come up with these interesting little oval shapes. Some of the little oval shapes are splotchy, and some of them are have just two kind of blue and orange lobes. One person made a little oval, a heart shape. Looks like one person is finally starting to... Hey, I found somebody that has my my model out there. Someone has actually put a file representing Milne's model on the Milne universe. Indeed, it looks like they're actually putting an explanation for inflation out there. In any case, this does look like somebody has basically got a, in principle, an idea of what I was about to talk about. The surface of last scattering, right here, being something that we can actually look at, and if we are here, then we would see a different color over here and over here. But what I was really planning to talk about in this video was the three basic explanations for the cosmic background radiation. There's three basic explanations. One is that the light is coming from fluctuations in the energy of space. And I don't know whether to call this a explanation or a misconception, but basically the idea is that for some reason there's quantum fluctuations all over in space, and they occur at a 2.7 Kelvin temperature, and that's where we see this 2.7 Kelvin background blackbody radiation. Okay. And then there's two other explanations. Both of them come from the idea that the light is coming from the surface of last scattering. And what I'd like to do is try to distinguish between these two different ideas. One of them says that the surface of last scattering is moving away from us at nearly the speed of light. And the other one is saying that the surface of last scattering is far away but not moving away from us. Now, this is the more common explanation. This is what the standard cosmological model says. Basically, in essence, it says that we are here and we're looking at, when we look out into the universe, we're looking back in time towards two events that happened far away from each other that both basically are associated with the Big Bang. And that this is the first time that these two like this particle here shot a photon away from that point 13.7 billion years ago, and it's arriving now. And this particle shot a photon 13.7 billion years ago, and it is first arriving right now. And indeed, that photon is basically the first photon it's sent since the beginning of the universe. And this is the first time we have ever seen this particle, because up until this point all of its photons had been underway, and now we are first seeing the photon at this moment in time. Now, this other version is the surface of last scattering is moving away from us at nearly the speed of light. Mainly in this space-time diagram, instead of having a triangle like that, we're going to have the particles themselves are moving at nearly the speed of light in either direction, and we're right here, and we're seeing the particle emit that point of light, and that particle emit that point of light. But we've been in continuous contact with that particle the whole time. We saw what it did here, we saw what it did here, we saw what it did here. We've been able to watch that particle, or basically we probably haven't been watching that particle. There's probably been stuff in the way most of that time, but in essence it would have been possible to see that particle follow that entire trajectory from the beginning of the Big Bang. In the standard model, you're basically in a situation where that particle was not in what's called causal connection. So in essence, at this point in time, this is the first time that anything that this particle has done has been causally connected to what is happening now. We've basically been, as far as we've been concerned, this particle did not exist until this light reaches us. In this version, the the particles the particle exists the whole time, basically, maybe moving in slow motion, but they exist the whole time. These two models also have different reasons why we see a 2.7 Kelvin temperature coming out. Basically, this has to do with black body radiation, Planck's law, the Planck distribution of light, and stuff like that. But we see a 2.7. We see a distribution of light as though the body we're looking at is only 2.7 Kelvin, which is a very, very cold temperature. Now, in the standard model, the reason that it's at 2.7 Kelvin is it was generated at 3,000 Kelvin. However, because all the time that photon has been underway, the space has been stretching. It arrives in it starts out at a very, very, very short frequency, and it comes out over here at a long frequency. So space has been stretching the photon that has been underway the whole time and causing it to stretch out to a longer wavelength. Now, in this version, there's only one effect causing the light to stretch. It's the Doppler effect. Basically, when you have something moving away from you very quickly, the wavelength is elongated. Now, there's a third thing. Inflation in these two different universes works a little bit differently. Inflation, according to some video I just watched, there's like several different possible explanations for inflation in the standard cosmological model. In this version, there's only one. There's exactly one explanation for inflation, and it is identical to the explanation for the twin paradox. Namely, if you have an object that's moving very, very close to the speed of light, and then accelerates suddenly, let's say this one is going off to the right near the speed of light, and then it stops, and it's moving that way. Well, the age of this particle is going to be determined pretty much by the length of that line there. The age of the universe is going to be determined by that line there. And he will go, hey, the age of this part of the universe here is like 13.7 billion years, but the age of the whole universe is like 40 billion years. In any case, inflation has a fairly simple, straightforward explanation in this other model. So you can decide for yourself which one seems the simplest. Is the light from the cosmic microwave background radiation coming from quantum fluctuations in the energy of space? Is it coming from stuff moving away from us at nearly the speed of light that we could have been watching the whole time? Or is it coming from non-causally connected stuff that is not moving away from us, but just became part of our universe because the space-time grew to encompass it? I personally think that this is the most simple explanation, and will probably eventually become more commonly accepted, or at least it will become understood.